Yeah. All right. So good morning. Okay, I really did miss you guys yesterday. And I have sad news. This is sad news. Some of you might get emotional. This is the time. Yeah, get your tissues out.
That was just funny.
Okay. Today, we start the absolute last new topic. Not new unit. Are you okay? Oh, that with the tears and why, baby Jesus, why? Okay. So today we start the absolute last brand new topic in the whole Calculus AB curriculum. We are testing on this unit next Friday, April 6th. We have the AP Summit happening at East End on Saturday, April 7th. And then we have 3 days together to get ready for your final exam, which is Thursday, April 12th. Right, your final exam, others are calling it the benchmark exam. I'm calling it the final exam because that's really what it is. We've got 3 days to review for your final, plus the Saturday. And then after April 13th until Tuesday, May 15th, we are in review mode. We're going to go back to old topics. We're going to revisit old ideas. We are there. We're there. Daisy, what's up?
What is it
Of course you're going to be here on the 12th. Okay, so...
When is the final to?
The final is Thursday, April 12th. Okay, so... Oh God, why God, why? Alright, so you might just want to get this copy down somewhere. So here's where we've been. We have been in the world of area, and I might say find the area bounded by these two curves. This is where we started the unit. This is what made things different. And I want to get some hands on this. If I asked you to find this area, how would you do it? What would you need? What would you go find? Henry, get me started.
You can do a different integral from, well, the first intersection point can be A, and the second one can be B.
Okay, we've got intersection points here. Here's A, and we're going to call this B. And you might find them by hand using some algebra skills, or you might go on the graphing calculator and find the intersection point. And are we all okay with both of these skills? All right, Henry, keep going. What are we going to do?
Then you can have the integral from A to B.
Integral from A to B. I'm going to stop you there, Henry. Somebody pick it up from here. You've got the integral. You found your intersection points. You're looking for area. Gonzalo, what are you going to do?
You're going to do top minus bottom, so it's going to be f of x.
We're going to do top minus bottom. Now, there's something that I think you're thinking about, but the words didn't really come out yet. There's something that needs to happen first so that you do this right. You want to look at that slice, that representative slice. So you look at this little rectangle, and the question is, how long is that? How long is this slice? And everybody knows how long this is. F of x minus g of x. Top minus bottom. How wide is this rectangle? What's the width of this rectangle? That's what we call the dx. This is an infinitesimally skinny little rectangular slice. How do I find area? I take the height times the base, f of x minus g of x, integrate the whole thing with respect to x. Is everybody's 100% okay? I would expect a problem like that. You got it. We're good. Okay, good. How does it change? Have a quick conversation with somebody near you. If I want you to find the area in the first quadrant. So this part over here and this part over here. Quick conversation. How does it change?
He's Adam.
You just add G of x. You do 0 to A. Add A, G of x minus f of x. And then boom, you get 100.
Okay, once you get your plan, break it for me.
Not me.
You just slip below 100 grand.
Flip a picture.
Okay. No, half.
All right. So I heard a whole lot of folks say, well, to find that total area, we're going to add them. So if we're doing an integral from a to b of f of x minus g of x, integrate with respect to x, what is it that I'm adding on to this, Jose?
You want the, you go from 0 to a.
Okay, we're going to integrate from 0 to a. And then what?
And then it's going to be g of x minus f of x.
G of x minus f of x, and we integrate with respect to x. How many of you guys had this as your setup? Okay, we're going to find the area for the first piece. You're going to add it to the area of the second piece. Hopefully we're doing okay. All right, last one. Now I want to look at volume. And some of you are already ready and you were telling me things about what you were going to do. Rebecca wasn't quite ready for what I'm about to ask though. I want to go back to this original region and I want to find the volume when I revolve around some line up here, y equals L. That's the goal. I want to revolve around this other line way up here. Questions that I would hope you would ask yourself first are,
Hollow or solid?
hollow or solid?
Hollow.
Imagine that region spinning around not your x-axis, but the line y equals L. Hollow?
Yes.
Everybody good? Okay, hollow. So volume, because this is hollow, it's going to be pi. Going to be an integral. We need the big radius squared minus the small radius squared. This is what we're looking at. Well, when I look to find the big radius, you always start on your axis of rotation. Start up here. And tell me when I should stop for the big radius. Stop here? Right, from your axis of rotation, you go out to the outside curve. And you're going to say, how long is that? Well, that's your big radius. Your small radius starts over here, and you're going to go to the inside curve. And so you need to ask yourself the question, what's the big radius? How long? How long is that slice?
L minus.
L minus
G of x.
G of x. Top minus bottom still. Length. Length in geometry is top minus bottom. Or if the rectangles went this way, right minus left. So the radius is L minus, what do we say, G of x? L minus G of x, the whole thing squared. Small radius. Small radius, we go from L to f of x. So L minus f of x, the whole thing squared. And limits of integration?
A to b.
A to b. And we're going to integrate with respect to x. And I hope everybody's okay. Destiny, you're good? Friends over here, we're good? We're going to get you there, Jeanette. But thank you for the honesty. All right, so I want to give you guys a little bit of reading time. On page 29, this is where we're going next. I've got a whole new world for you. Don't make me sing the song. I would ruin the movie for you forever. And I've got props. We've got Homer. And we've got Superman. Give it a read on page 29. We're going to talk in a little bit. And Paul, then I'm going to need you to drive the laptop, okay?
So you do another? No.
Okay, Homer pass.
That's oddly weird. For the past few days, we have original objects, which are generated by removing or making time on the x-axis. We have approximated the modern music selector, whose order can be found in the right?
Will you play the man?
Then apply our knowledge to limits and the integral to generate the integral expression
That's day at 5 p.m. The rejection letter.
We have modified this integral expression so that we can find the volume of solids by revolving around the y-axis, any horizontal line, or any vertical line. We have also scored three-dimensional objects, which are composed of one or more functions being revolved around the x-axis. The key to solving all these problems is to think about the representative. The key to solving all these problems has been to the represented triangles and cylinders squashers are generated. Where are we going? Now we move to the kind of solid for the next few days to solid foods. Cross-sections are squares, rectangles, semicircles, ellipses, isosceles, rectangles, and various other friendly geometric. I think that's sarcastic. The process will be the same.
Alright, we're going to pull it together in 3, 2, and 1. Alright, so today we leave the world of area and volumes of spinning objects, and we're going to look at solids that don't have volumes of revolution. Like, you might be looking at Homer's belly and say, gosh, he looks like Mr. DeRozier. First, don't say that out loud, that's rude. Homer Simpson's belly is not an example of a volume of revolution. Why? Why? Marilyn, why? Because what? It's a 3D object. There's a different reason why this is not quite the same as this volume of revolution over here. Jeanette, what's different? We're only doing half of a revolution. We're not going 360 degrees. We're only going to go halfway. So instead of thinking about slices that are cylinders, we're going to think about slices that are, what's the name for the shape? Well, the slices are semicircles, right? Okay, well, great. That's Homer. What about Superman here?
Semi-pyramid.
Semi-pyramid. Look at those slices.
Square.
Now, depending on how well these are done, these slices are either squares or they are rectangles. Okay, I'm going to pass both of them around so that you can like take a look at it. You can see it. A lot of the geometry is going to change. A lot of the calculus is going to stay the same. Paul, you're going to take us into this whole new world. Gonzalo, can you turn the front lights off, please? There you go. So there's nothing that you need to do right now. I just want to like show you the stuff, and you can ooh and ah in all the right places. Ask your questions. Then we're going to do the calculus. All right. So what I've got is my base. My base is this circle, the flat region. We're just starting there. And we're going to talk about the three-dimensional object that's formed by taking slices, and the slices are either going to come out of the board at you like this, or come out of the board at you like this.
Wow.
Okay? Now the hard thing, and this is where high school calc, I completely had no idea what was going on, is visualizing the three-dimensionalness. Okay? So to help along the way, we've got Geometry Sketchpad. And Paul, I want you to drop y-axis flat.
Wow.
So the perspective, you've got your x-axis. The y-axis was the thing that was going vertical like it always does. We dropped it flat, so now it kind of goes back into the board. This axis over here, any guesses?
What? I mean, Z.
Yeah, not the y, we already have a y-axis. This is the z-axis. When you go into 3 dimensions, you have an x-axis, you have a y-axis, you have a z-axis. Paul, I want you to show me 4 squares. The squares are the slices, the way that I'm slicing. You're going to slice so that your square goes from one side of a circle all the way to the other. That's going to give you some sort of a length. You're going to make a square. Well, if it's a square, however long this is, that's exactly how tall we're going to be. And then there's going to be some sort of a thickness. Now, we're not going to do just one square slice. We're not just going to do 4 square slices. How many square slices are we going to need to get the full volume?
Multiple.
Multiple and infinite number of slices. Okay, Paul, can you show me sweep one square? Check it out. So that's representing one square as it moves from one side of your circle all the way to the other. Paul, can you click on Create Solid? I was hoping for oohing and eyeing, but I guess not.
Wow.
Yeah, that was pitiful.
I mean, I was already oohing
Making me
and
beg
eyeing.
for you were oohing and eyeing in your heart. So that's what the solid looks like. Paul, click on Show Solid. This is the three-dimensional solid that we're talking about. New vocabulary terms. I see, Sylvia. Give me a second. You have the base. The base is what you're building on top of. What was our base in this case?
Circle.
The base was the circle. It's the flat part. Then you have your cross sections or your slices. What are the slices in this case?
Square.
The slices are squares. We're going to have conversation about which way do you slice. Do you slice perpendicular to the x-axis, or do you slice parallel to the x-axis? And then finally you have like the object itself that we're going to try and find the volume of. Paul and Karina.
So certain shapes always have the same slices?
One more time.
Like certain shapes always have the same slices?
The objects that we're going to look at, I'm going to define the base for you, and then I'll tell you about the slices. We could do squares, you could do other friendly slices, like semicircles, like right isosceles triangles, like equilateral triangles. But it'll be one consistent slice for the whole shape. Karina.
How would it look if it was perpendicular to the y-axis, like different?
That's a great question that I'll get to in a little bit. Sylvia.
So, since it started off as a circle, but our slices were squares, that's why it doesn't look like a sphere?
That's why it's not a sphere, because you're not spinning the base, you're using the base to make your cross sections.
Oh.
Okay? So let's look at the same base one more time. So Paul, go over to tab number 2. Okay? And this time the slice is going to be equilateral triangle. Okay? So Paul, let's drop the y-axis flat. Equilateral triangle. What do we know about an equilateral triangle? All sides are the same. A geometry teacher would hope you'd use a better word than the same. All sides are equal. It begins with a C. Congruent. Jackie, okay back there? All sides are going to be congruent. All right, so show me 4 equilateral triangles. Okay, we've got 4 equilateral triangles. Look at that. That was that much. Okay, and show solid. Okay, different shape. Different shape, different volume. We're going to talk about the calculus process of figuring this all out. All the friends okay?
Yes, why don't we want to?
Why would you want to do this? Why wouldn't you want to do this?
Real life, like why do people?
If you look at some of the buildings that are downtown, and I unfortunately did not pull up any pictures and I should have done that in advance, buildings are getting much more sophisticated in their design. They're not just like a box or a rectangular prism. Some of them are starting to get like some twisting going on, especially towards the top. Buildings want to stand apart from one another, and so they're looking at much more complex architectural design. Yeah.
So, whenever we're gonna do it without a calculator, we're gonna have to figure out how to do it.
Oh my God, Andy, what a great segue. It's like you read my lesson plan in advance. Thank you for that. Let's look at the first problem. You got this. All right, we're going to do one together, and then you guys are going to get some practice, and it's all going to be okay. And Gonzalo, if we can turn the lights back on. I am not going to give you the pictures in most of these cases. But that's okay, because you're like super smart. Super smarties, we get this under control. What I am going to do is I'm going to describe for you the base. The base is what you're going to start with. Where'd Homer go? Homer, where'd Homer go? Okay, it's over here with Chris and Mars. Okay. For Homer, the base is the flat part. It's the part that's on the foam board. And then you're making slices, and these slices are going to be semicircles. For the Superman symbol, the base, it's the flat part again. So this is going to be your base. The slices are the squares or the rectangles. Okay, Henry.
Isn't that exactly what like 3D printers do?
This is exactly what 3D printers do, yes. And if somebody's wondering, like, what would be a great birthday gift for me? A 3D printer. I take it. All right, here we go. The base of a solid is the region bounded by the graphs y equals e to the negative x, y equals negative 1, x equals 0, and x equals 1. That's your base. That's the flat that we're building on. Each cross-section perpendicular to the x-axis is a square with one side in the xy plane. Determine the volume of the solid. This is what these problems are going to look like and feel like. So let's start with the base. What do we know?
It's
Square.
y equals negative x.
It's bounded, so it's trapped by y equals e to the negative x, y equals negative 1, x equals 0, and x equals 1. Take a minute, sketch that base for me. Let's make sure we all know what we're looking at. And these are friendly shapes that you should be okay with. E to the negative x is a decreasing curve. Y equals negative 1. There's my line. X equals 0. That's your y-axis. X equals 1. There. That's your base. That's the flat that you're building off of. Yeah.
When we do this problem, do you want us to like have the y-axis like flat or like?
So when I'm gonna draw it, I cannot do the whole like drop y-axis flat. We're not gonna worry about drawing the three-dimensional object. That is beyond my skill set. So if you can do that, God bless you. Okay, this is the base. We get the curve, we get the line y equals negative 1, we get x equals 0, we get x equals 1. Great, that's the base. Now, tell me about the slice. What do we know about the slice?
It's a square.
Square, and what was the other thing? Perpendicular to the x-axis. Can you guys show me with your arm perpendicular to the x-axis? Perpendicular to the x-axis. Here's the x-axis. Perpendicular to the x-axis is... Perpendicular to the x-axis is this way. Okay? So your slice goes this way. I'm going to call that slice L. How thick is this slice going to be?
DX.
This is a dx slice. This should be just like we did with area, just like we did with volume of revolution. Dx. Okay? So, one more time. Show me perpendicular to the x-axis. Okay? And this is a dx or dy? Dx. Okay, so when I say perpendicular to the x-axis next time, I get an arm and dx. Okay, one more time. Perpendicular to the x-axis? Dx? Good. It's like a karate dojo. Hold on. That's the slice. Adrian, I need your help with this. You are my slices. You are going to control my slices. I need the square. The goal is to help you with the visualization here. Here's the slice in the base. The square, what do we say, dx or dy? Dx comes out of the board. This is helping you to do the visualization. So however long this is, how tall is the square?
DX.
How tall? How tall? How long is this side here?
L. L.
L is how long this piece is that touches the base. How tall is the square?
L.
It's also L. It's a square, duh. Okay. So here's what I normally do. I draw the slice. There's my square. This is L. This guy over here is L. But my square has some thickness to it, so I want to draw a slice with a little bit of thickness. It has a length of L, it has a height of L. How thick is the slice? Dx. So now I'm going to ask the question, what's the volume of one slice? L this way, L this way, times dx. So the volume of the slice is L times dx, or L squared dx. And I hope everybody's still okay. You got the base, you got the slice, but I'm not interested in the slice. I want to know, what does this object look like that's made up of all these slices?
Okay.
So how do I find the volume for the solid? We figured out the volume for one slice. One little slice has a height of L, comes out L times dx. Jackie, how am I going to find the volume for the solid? You're going to what?
I'm gonna say sigma.
Not sigma. I mean, you're there.
Is it the E one? Is it not a sigma?
What's that wiggly thingy?
Oh my God. I go away for one day and I hear the squiggly thing.
Integral.
How about an integral? Because the integral is, as Jackie said, it's a summation. Okay.
Squiggly thing.
Where do we start summing?
Zero.
0. Where do we stop?
1.
1. What's the integrand, the setup?
The pi.
L squared dx.
L squared dx. Now here's the thing. Here's the thing that we have not done. What's L? How long
The number.
is L?
No, because you're gonna keep changing.
You're right, it changes. L is different here than it is here, than it is here. But the way that you find L is the same everywhere. Flora, how long is L?
Is it y equals e to the negative x
E to the negative x
minus
Oh.
equals negative 1?
minus negative 1. Right? Do they all have the same setup? They all go from top to bottom, top to bottom, top to bottom. So your length is this e to the negative x plus 1. So your integral is an integral from 0 to negative 1, e to the negative x plus 1 squared. That's the setup. That's the part that's different with volumes with these sections. Yes, ma'am.
So we don't need pi anymore?
Thank you for being the kid that asked. I knew it was going to, my bet was that it was going to be Daisy. Daisy, what was your question one more time? What was your question one more time?
Oh, so we don't need pi anymore?
You don't need the pi in front?
No.
Why not?
Because it's not full.
You're not, Kevin? What? What? It's not a cylinder anymore. The slices aren't cylinders. Yeah, honey, that's why you need a pi. But that's why, stay with me. Stay with me on this one. You always spend the time on the base, because you got to understand the base. Then we have a conversation about the slice. The slice used to be a cylinder. The slice is now a square with thickness. And then you go to the volume of a solid. Take a minute, pop this into your calculator, show me that you get this.
So when you put a piece of pie out, it will come cake?
Oh, Henry, with you, we're going to go all the way. You're squaring it over there, honey, because L is the length of the slice. But the way I find the volume, square, the length and the height are the same, times the thickness. Sheila them home.
Oh, I see what you mean.
Calculator.
It comes partially.
We're not doing
Oh, I remember.
Yep.
So do you remember like a couple of days we did like rotation of the x-axis or
Yeah, you got the easy bit.
With these, we're not going to have conversation about spinning.
so it's like a
It looks like
Right. I'm going to always describe for you the base, the flat, and rather than asking the question, what happens when you spin, the question becomes, what happens when you build up off of this? This is the ground and the slices come this way.
Why don't we build the other way?
Why don't you build the, like into the board?
No, like you know how this, like we're cutting it like this, why don't we do like that?
She said she's.
Oh, like stacking your slices this way?
That way is
Like this way?
Yeah.
Yeah. We could absolutely do that.
Okay.
We could absolutely do that. All right, what are we getting for 2.696 seems to be popular. 2.697. Okay,
Up in the square.
2.697. Just quick, honest show of hands, how many guys have 2.697? You have a good, loving relationship with your calculator. Good. Try the next one. See what you can do.
Pay for our brain.
You don't need to pray for your brain. You have smarticle particles.
My smarticle particles died, and we haven't noticed what's like. I think you're gonna notice.
Take the time to understand the base. Go.
It has triangle and closed line.
Correct.
Right?
Laura's got a good base. She understands the base.
Negative x plus 1. It's just one up. It's literally
Marilyn understands the base. Rebecca's getting there. Michelle's got it.
Yeah. X plus 1.
We're going all the ways. Okay, Jesus understands the base. A solid has the triangle enclosed by x plus y equals 1, the x-axis, the y-axis.
Whatever.
I know. I made it.
All the sides. Only 2.
Okay. Everybody seems to be doing pretty well with the base. I want you to invest the time doing a quick sketch. Don't go all OCD on me. Just a quick sketch of the base. Next conversation we have to have is about the slice. Rebecca, what do we know about these slices? Or cross sections? Okay. But you gotta be careful, there's a lot of triangles out there. What do we know about these slices? They are right isosceles triangles. And one more thing. Which way? Show them perpendicular to the x-axis. And I want to hear it. I want to hear it. dx. dx. Your slices, Adrian, you ready?
Yeah.
These are your slices right here. The tough part is you're like, but wait, that slice looks just like the square slice. That's why I need this next piece. A right isosceles triangle. A right isosceles triangle is going to look like this. I realize that this is not the right size. Is everybody okay?
Yeah.
Okay. We got this guy here coming out. Well, how long is this? This is L. If it's a right isosceles triangle, this leg here is L. How long is this leg? L. How thick is the slice? dx. So I'm going to draw my slice this way. Right isosceles triangle, L, L. Give it a little thickness. Give it a little thickness. And now the question is, what's the volume of the slice? Talk to somebody near you. Think back to geometry. How would you find the volume of this slice?
No, you have to find that. Just to find this side. Find this side.
We got the slice. Nice. Okay. All right, man. Let's pull it back together. The volume of a shape like this from 8th grade math, I was just over there visiting with Miss Lewis's 8th graders. They know that the volume of the slice is base times height. The base is this part over here. How do I find the volume Or how do I find the base? Well, it's a triangle. 1/2 times your little base times your little height times your thickness. What, right? Some of you maybe went straight to base times height divided by 2 times the dx, because the dx is your thickness. So your volume here is 1/2 L squared dx. Now that you've got that, go get me that solid. Get me that solid, we'll talk in a bit. I want to see the setup. Once you've got the setups, get into your calculator. Yep, dear. But if you understand the geometry, you're going to be okay.
1/2 times
Okay, we're doing an integral. Everybody knows we're doing an integral. Where do we start? Where do we end? Where do we start integrating? Where do we end? Well, I start right over here at x equals 0. I end over here at the root x equals 1. Most folks seem to have that. We're good. And then it's 1/2 L squared dx. The only thing I need to know at this point, how long is L?
1.
You want to be careful. I heard somebody say 1. Over here, it has a length of 1. And over here, the length is 0. But what about all these slices in between? They're always the top function
Why minus 0?
minus the bottom function, which the top one is negative x plus 1 minus 0. You don't have to write it that way. You could just go straight to negative x plus 1 because you're starting on the x-axis and you're going up to the line. So that's L. So your setup is an integral from 0 to 1, 1/2 negative x plus 1 squared dx. And tomorrow and Thursday, we're going to practice on the integration by hand. Today, I just want to go deep with the setups. So if you haven't done it yet, plug this into the calculator. Get me that number. Good. Looking good. 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 Keep going. Keep going. If all goes well, you get 0.1667.
Weird.
Wondering, anybody know the fraction name for that?
So we're always going to use a calculator?
No.
5/3.
5, oh my god. 5/3.
It's 1/6.
This is really 1/6. And I know that you all have the skills to integrate this, but I want to focus on the new part, which is like understanding the region and the setup. Alright, see what you can do the next one. Oh, I'm so excited.
He's excited. I'm not excited. Not really. Just got a date. Did I think this is oh, she doesn't normally have
Good stuff's coming.
I think. Here, I'll show you one. You take plastic.
I should try to layer.
I only have plastic.
Hi there.
Would it be, 2 minus x? 2 minus x?
I know it's
Just let's do that.
You stumble through your words.
Okay, I'm gonna leave it at
All right.
But the thing is, this is plus and minus.
A solid has the circle x squared plus y squared equals 4 as its base. And I know we talked about this last week. All circles have that standard form, x minus h squared plus y minus k squared equals r squared. You do not have to have that memorized. You don't have to have it memorized. But from here, you should be able to tell me the center, and you should be able to tell me the radius. Where's the center for this circle?
0, 0.
0, 0. Where's the rate? What is the radius? Square root of 4, which is 2. So here, you're going to go 2 to the right, 2 up, 2 to the left, 2 down. Beep, 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 beep. Beep, 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 beep. That's your base. That's the flat part that we build off of. Okay? Now, you might want to label some other points, right? The radius is 2, so here's 2 comma 0, negative 2, 0, 0, 2, 0, negative 2. Sure, that's great. Now we got to move on. Do we understand the slice?
Yeah.
Do we really understand the slice? And some of you are like, no, I don't understand the slice. Axel, can you read about the slice or the cross-section for me? What are we doing?
If cross section is taken parallel to the x-axis, a rectangle side is 4 times the length.
Cross-sections taken parallel to the x-axis are rectangles whose height is 4 times the length. Which way are we slicing this time? Parallel to the x-axis. Can you guys show me parallel to the x-axis? Parallel to the x-axis, so what?
dy.
dy. Right? So one more time, parallel to the x-axis? dy. Perpendicular to the x-axis? dx. Parallel to the x-axis? Perpendicular to the y-axis? Y'all don't listen. Perpendicular to the y-axis? Here's the y-axis. Here's perpendicular to the y-axis. dy. I'm tricky. Don't worry. I'll be warm for eternity because I made you miserable. Here's your slice. Parallel to the x-axis. There's your slice. It's a dy. Adrian, help me out here. Thank you. I need rectangles. Hold on, Andy. Now you're going to be like, wait, this is stupid. Okay, this is just a representation. There's the bottom part of the rectangle. How far out do I come?
4 times.
However long this is, how far out of the board?
4 times the length.
4 times that length is how far I come out for each rectangle. I wish Mr. Paiva, my calculus teacher, had spent a little bit of time on this. There's the length, come out of the board 4 times, whoop, and go back. That's why I like to come over here and draw the slice separate. Here's my slice. L, how tall? 4 times L. It's got some thickness, just like me. How thick? What's the thickness? dy. Volume for one little baby slice. One little baby slice. Well, this looks like a rectangular prism to me. So L times 4L times dy, or even better, 4L squared dy. That's the volume for one slice. If you understand the volume for one slice, this next piece cake. Yeah, Laura. So good. You should stay forever. We got the base. We got the slice. Go get me your solid. Your solid is going to be an integral of 4 times L squared dy. 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 Okay? Okay, limits of integration. Where do we start? Where do we end? Negative 2 to 2?
No, it's a y.
Y's start down here, slice, 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 all the way to the top. Y equals negative 2 to y equals 2. This is a good setup. It's got a lot of good pieces that I care about. Floor, what was your epiphany? If this is going to be a dy integral, you need to write this circle in terms of y. Meaning you're going to start with this x squared plus y squared equals 4. And we say in terms of y, but it really means solve for x. So to solve for x, we're going to subtract y squared. We're going to take a square root. And we're going to have the positive, and we're going to have the negative. Now we've only got 1 minute. X equals positive square root of 4 minus y squared is the right part of the circle. The left part of the circle is where x has the negative values. So x is the negative square root of 4 minus y squared. How long is L? Well, L goes from this side to that side. So it's, we're used to thinking top minus bottom, but we're doing a slice this way, right minus left. So this is square root of 4 minus y squared minus the negative of the square root of 4 minus y squared. Stay with me just for a second. So that's really 2 times the square root of 4 minus y squared. From there, all you do is replace L with what we determined L to be, pop it into the calculator, and you'd be done. We're going to spend the next couple of days on this. You're going to get really, really good. And if not, there's always next year. Both. Because the positive is the right half of the circle and the negative describes the left half of the circle. It's just,